Hello everyone, Assalamualaikum and very good day to all of you. Today we are going to learn about engineering materials, which is under topic number 5 in our syllabus. First of all, let's begin our lesson with this short video clip.
Materials are all around us. It makes up everything that we use from day to day. But one thing a materials engineer will do is try and make those materials better.
I think material science and engineering is basically when engineers take materials that are in everyday use and we look at it in the microscopic scale and the atomic scale and then try to enhance them into like our macro scale everyday materials that we use.
You use materials everywhere. We're currently standing in a building made of materials, made of concrete and steel, and all of those had to have been studied at some point in order to know that they are the most structurally sound materials for this application.
Everything in the world is made up of materials, right? And those materials, what we see macroscopically, like a piece of steel, just looks like one hunk of steel to us, but actually there's a bunch of little particles that it's made up of, and how those are arranged changes how strong the steel is, how easy it can bend when it melts and things like that. So material science and engineering is actually controlling that so that we can change how strong the steel is or anything. We also do polymers and plastics, ceramics, and electronic materials also.
Using science and engineering to make everything better in our world.
We can look at a failure of a piece and determine why it failed, how it failed, if a similar piece that's in use will fail.
The more efficient we can make batteries, it'll help consumers a lot.
We need things that are more efficient with energy, we need things that are recyclable, or even such things as being tougher, stronger, more resistant to corrosion, environmental things. So it can span pretty much all spectrums of industry out there in the world.
We have higher demand for electronic components that need to be smaller and lighter. So you need to come up with new materials that can handle such capacities.
There's only a certain amount of different elements in the earth, and a lot of things that we use to make things like TVs and electronics and things like that are limited. So if we can figure out how to recycle them and reuse that, it'll be more cost effective.
Another realm of materials that's going to, I think, be on the rise in the future is going to be multifunctional materials.
Life cycle, the whole system. What's going to happen to this in the end? Things like plastics and stuff, a lot of people are worried about landfills and things like that they don't break down very well. So there's people working on polymers that are made out of biomaterials like corn and potatoes and things like that will actually biodegrade.
I feel like I have so many options to choose from and so many different areas I could go to.
To make technology greener and as well keeping it friendly enough for everybody to still want to use in everyday applications and not make it a big hassle for everybody to become a green society.
Ames Lab is located on the edge of campus and it allows a lot of students to have research positions with professors or scientists to allow them also the opportunity.
The visit I had to Iowa State sold me. The department up here is one of the most up-to-date, I think, advanced laboratories we have for materials engineering, and then the community we have, the access we have to professors and research and things, is just an opportunity you can't pass up.
From the video, now we know that every segment of our daily lives are influenced by materials. Do you agree with me? As you can see from the slide, there are a bunch of materials that engineers use just to make this car. Okay, different materials being used for different aspects and different system of the car. Why? Because different materials possess different characteristics and properties that allow engineers to utilize that properties and characteristics and assemble it, manufacture it, and hence creating this amazing car. Okay, now take a look at the slide. Let's begin with the types of engineering materials. Now, engineering materials are classified into two main categories. which are metals and non-metals. Our focus for today's topic is on metals. For non-metals, we will cover on next video. Now these are the learning outcomes that you should be able to understand once you complete this topic. But for today's video, we will cover item 5.1a and 5.1b as stated here. Define ferrous metal and give examples of ferrous metal such as iron and steel. Now imagine that, suppose that you are appointed by your employer to design and build a smartphone with minimal production costs and resources, and that smartphone need to be sold in the market within 6 months. How would you respond to this situation? Quite tough, isn't it? And that is why we need to study materials so that we can select the right materials for the right product, right? Now take a look at the slide. Many engineers, whether mechanical, civil or electrical, will at one time be exposed to a design problem involving materials. Now the problem is selecting the right material from the many thousands materials that are available in this world. Okay, for that you need to meet these following criteria. Okay, what are the properties of the material that you need to select? The deterioration of the material properties that may occur during service operation, and the most important factor, probably the costs and resources involved to obtain the desired materials. Take a look at ferrous metal. Now ferrous metals are defined as material with iron element as the base metal. Okay, iron. The properties of ferrous metals may be changed by adding various alloying elements such as maybe nickel or molybdenum and so on, in order to alter the properties. Products of ferrous metal such as plates, bars and sheets can be found in many products. So examples of ferrous metals are steel and iron. Okay, steel and its alloys and iron with its variation are among the common ferrous metal used in engineering field. Now, in general, these are some of the properties possessed by ferrous metal. As you can see here, ferrous metal, the general properties is durable, has a great tensile strength, usually magnetic, low resistant corrosion, can be recycled, and good conductors of electricity. Now these distinguished qualities make the ferrous metal usable in building constructions as well as in making tools such as for the hardworking tools, vehicle engines, pipelines, containers and so on. Okay, in this part of presentation we will focus on iron and its types before we move on to steel on later slide. Okay, focus on iron. Now iron can be categorized into two types, which are cast iron and raw iron. Now before I explain further on cast iron and raw iron, here is a brief overview of iron itself. Iron is the basic constituent of steel. The main ingredient of steel is iron. Okay, iron is actually the most rich metallic minerals in Earth's crust after aluminium. Can be found in the form of ores as oxides, carbonates, silicates, and sulfides. Now, in order to produce iron, we need to produce it in special equipment such as blast furnaces. Carbon exerts the most significant effects on the microstructures and properties of iron product. Okay, we take a look at these carbon properties and what will happen to the iron when we mix carbon. Increase in the amount of carbon will decrease the melting point of the iron. Okay. Now the term exert here is the influence factor. Whether the steel is ductile or hard or tough, it is depending on the carbon content. Now, before we conclude our today's lesson, take a look at this video explaining the process of iron making in a blast furnace and what conclusion can we draw from the video. Please write your answer in the comments section. Thank you and have a good day.
Iron ore mined from the Earth's crust contains impurities such as sand, rocky materials, limestone, etc. The impurities are collectively known as gangue. The gangue must be removed before the metal can be extracted. The process by which impurities are removed from the ores is known as concentration or enrichment. To begin with, the ore is crushed into small pieces in a crusher. The crushed ore is then powdered in a grinder or pulverizer. The powdered ore is then washed in a current of water to remove impurities. The heavier ore particles settle down while the lighter impurities are washed away with the water. The concentrated ore is then subjected to a process known as calcination. The ore is heated strongly in the presence of air in a reverberatory furnace. Besides converting the non-oxide compounds in the ore to the oxide, roasting helps in removing moisture and organic matter. Impurities such as carbon and sulfur are converted to their volatile oxides which escape. In addition, ferrous oxide present in the ore is oxidized to ferric oxide. Let us now see how iron is extracted from the roasted iron ore. The process of extraction of iron from its ore is known as smelting. The roasted ore is mixed with coke and limestone. What roles do coke and limestone play? Coke functions as the fuel, at the same time gets converted to carbon monoxide required for the reduction of the ore. The limestone acts as a flux. A flux is a chemical substance which combines with impurities and forms a fusible slag. The charge is brought by trolleys or skip cars over a conveyor system and introduced into the blast furnace through the cup and cone arrangement. The molten iron collects at the bottom of the furnace and is tapped periodically. It is poured into sand molds and allowed to cool and solidify. The iron obtained from a blast furnace is brittle and is called pig iron. Note, the term pig iron comes from the time when the molten iron was fed into molds from a common runner. The whole arrangement looked like a sow suckling its piglets, with the runner being the sow and the molds the piglets. The solid iron ingot removed from the molds were therefore called pigs. The unused carbon monoxide along with nitrogen from the hot air and carbon dioxide pass through the outlet at the top and enter the dust catcher which removes dust and other particulates. The dust-free gaseous mixture is burnt in special burners and the heat produced is used to heat the air that is blown into the furnace. The processes of addition of charge and removal of molten iron and slag goes on day and night for years. The blast furnace is shut down only when the fire break gets worn away and needs to be replaced.